Chapter 6, Part 1, Chirality. First up, we're going to discuss what chiral means and also compare it to achiral. A chiral molecule or object is not superposable on its mirror image. It is asymmetric, and examples include your hands and your shoes. So for example, these are gloves to represent hands. A glove or a hand is a chiral object because there is no plane of symmetry running through a hand. If you run a mirror plane through a hand, you will not find a mirrored thumb on the other side. You will not find a mirrored pinky on the other side. So a hand does not have a mirror image running through it. However, your other hand is a mirror image of the first hand. So your left and right hands are mirror images of each other. And those mirror images are not superposable, meaning you cannot lay one on top of the other and have everything match up. Your thumb will be over here, this thumb is over here. Pointer ends up on top of pinky, etc., right? These are not going to line up. So that's what it means for something to not be superposable. An achiral molecule or object is superposable on its mirror image and is symmetric. So it could have a plane of symmetry or a mirror plane running through it. Examples include a molecule of water or socks. So a water molecule, the electron pair is being drawn kind of in 3D here. So this pair is coming towards us, that pair is going away from us. There is a plane of symmetry running right through the molecule. You could also draw a mirror plane that separates the two lone pairs, and that would also show you how water is symmetrical. You could take a molecule of water and place it on top of another, and everything would line up. And similarly with socks, most socks, as long as they are not left and right in some way, but your typical average sock, if you were to take both of your socks off your feet and throw them in the air and catch them, you would have no idea which one was originally on your left foot and which one was originally on your right foot. So socks go on either foot because they're achiral objects. Our next definition is stereocenters. A stereocenter is any atom bearing different substituents such that interchanging any two substituents would create a stereoisomer. So in these first examples here, we're looking at either one of the carbons that are being given dashes and wedges here. So looking at the one that actually was changed, it doesn't look like it was changed because it's still a methyl group, but what we mean by interchanging is there's a hydrogen here. If we take the methyl and we switch it to be on the bond that the hydrogen is on, and we put the hydrogen on the wedged bond, we have now created a different version of this molecule. This first one is cis 1,4-dimethyl cyclohexane. The second one is trans 1,4-dimethyl cyclohexane. So these are different molecules, and the only difference between them is the 3D shape at that stereocenter. Another good example of stereocenters include alkenes. If we were to take this chlorine and swap it with the position of this hydrogen, we would actually end up with the molecule that's on the right. So cis and trans isomers can be considered stereoisomers of each other because by swapping out one of the atoms, you're able to create a different isomer. Our next term is chiral carbons or chiral center. A chiral carbon is a specific type of stereocenter. So stereocenter is kind of a broad umbrella term, and underneath that is this specific concept of a chiral carbon. A chiral carbon is an sp3 hybridized tetrahedral carbon atom bonded to 4 different groups. Emphasis on different. All sp3 carbons are bonded to 4 groups, but we are looking for 4 unique groups. So it could be that you have a hydrogen, a methyl, an ethyl, and a bromine attached to that carbon. As long as they are different, it would be a chiral carbon. Often you'll see chiral centers designated by marking them with an asterisk. So for example, in this alcohol, we have a methyl group, we have a hydroxyl group, we have a hydrogen, and an ethyl. So this carbon is chiral, and it's been designated with an asterisk. Molecules that only have one chiral center are automatically chiral themselves, but not all molecules that have chiral centers are automatically chiral. So for a molecule to be chiral, remember chiral is kind of a fancier way of saying asymmetric. Achiral is a fancy way of saying symmetric. So for a molecule to be chiral, a molecule must have at least one chiral center, and it must lack a plane of symmetry. So the next question is, are the molecules below chiral or achiral? Go ahead and pause and take a second and see if you can figure it out. So looking at this first molecule, we're analyzing this carbon here. This carbon has a chlorine, a hydrogen, and then two methyl groups. These two methyls are identical to each other. So this creates a plane of symmetry through the molecule. It's hard to tell because we drew it in 3D here, but if you were to draw a line through this carbon, it would actually split through the chlorine and through the hydrogen, which are really more stacked on top of each other than this image implies. So this is achiral. On this next one, looking at this carbon, we have a chlorine, a hydrogen, a methyl, and an ethyl. These are 4 different groups, and therefore this molecule is chiral. And so is this carbon. I'm gonna make that cleaner, a little star. On the next molecule, we have multiple carbons here, and we also have multiple carbons that have dashed and wedged bonds. So we need to kind of look at all of them and make sure that we do or do not have chiral carbons here. So looking at this first one, we have a methyl group, we have a hydrogen that wasn't drawn in, we have a bromine, and then we have this entire other piece of the molecule. That is 4 unique items. So this bromine carbon is chiral. And similarly, the other one actually has the same 4 things attached to it. So bromine, hydrogen, methyl, and then all the rest of the carbon. So the other one is chiral as well. So we fulfilled the first category. We have at least one chiral center. We need to check this one. Also, this carbon has a methyl, a hydrogen, and then this piece is identical to this piece. So those are not 2 unique things. Therefore, this carbon is not chiral, but that's okay. We already have 2 chiral carbons. Now we just see if the molecule has a plane of symmetry. Now, since we have this achiral carbon that's smack dab in the middle, that actually provides our plane of symmetry. These 2 pieces of the molecule are identical to each other. So this molecule is not chiral because it has a plane of symmetry. So it's achiral. Taking a look at the next one, we've already kind of done this one. It looks really similar to the other one. So we know these 2 carbons are already chiral. That has not changed. What has changed is the directionality of this bond. So now, if we were to draw an attempted plane of symmetry through the middle of the molecule, this side does not match this side anymore. And so this molecule actually is chiral because it is lacking a plane of symmetry.